Hi everyone, and welcome to the first of 5 videos going through some past exam questions on buffer solutions. I wanted to do quite a few videos on this topic because the questions come up quite a lot and it's usually something that people find quite difficult. So I wanted to make sure you've got plenty of examples that you can look through. So in this first question, it's saying we've got a buffer solution that's based on methanoic acid. First thing is explain what is meant by a buffer solution. It seems like a good place to start. Okay, what actually is a buffer solution? What's it for? What does it do? Okay, so a buffer solution basically is there to try to maintain the pH. Okay, so a buffer solution is a solution that minimizes pH changes. Okay, it doesn't keep the pH exactly the same, so we need to be really careful with how we're wording this. You cannot say a buffer solution is something that keeps the pH the same or maintains the pH. It minimizes the change. Okay, so the pH will change, but it won't change very much. Okay, and it's not magic, right? It minimizes pH changes when small amounts of acid or alkali are added. Okay, if you add loads of acid to it, it's not going to be able to cope with it. The pH is going to change massively. But if you add small amounts of acid or alkali, then it will minimize the pH change. So we've done that. We've explained what a buffer solution is. Now we need to describe how a buffer solution based on methanoic acid can act as a buffer. Okay, so we kind of need to include this. Let's just do this in bullet points to make it clearer. So a buffer solution contains a weak acid and its conjugate base. And so you end up with, if we're doing methanoic acid, for example, we're going to end up with an equilibrium setup. So methanoic acid is going to be HCOOH. And it's going to form, because it's a weak acid, it's going to form an equilibrium between the methanoic acid and methanoate ions. Okay, and a buffer solution is basically the mixture of these two things. Okay, so how does this help to minimize pH changes? Okay, well, when acid is added, the H+ ions from the acid can react with the methanoate ions that would be there in our buffer solution. And so what would happen is we'd be doing the backwards reaction here. So the equilibrium would shift to the left. It would use up all of the added H+ ions, and you'd end up minimizing the pH change. You'd go back to almost the same pH that you had before. Okay. So when acid is added, the H+ ions react with the methanoate ions, and the equilibrium shifts to the left. What about when alkali is added? Okay, so this is us explaining the buffer solution, right? So we're doing this bit. We've done half of it. What happens when you add acid? Now what's going to happen when you add alkali? When alkali is added, the OH- ions react with the methanoic acid. Yeah, this is the idea behind the buffer solution. If you have a solution that contains both of these, the methanoate ions can react with any acid that's added, and the methanoic acid can react with any alkali that's added. And so it will minimize pH changes. So the OH- ions would react with the methanoic acid, and therefore the equilibrium would be shifting to the right. Okay. Because we're going to end up using up the methanoic acid. Okay, and so therefore our buffer solution can minimize pH changes when we're adding acid, and it can also minimize pH changes when we're adding alkali. Okay. And that's a fairly common question. As we go through more of these questions in later videos, you'll see this question come up quite a bit. This sort of long answer is sort of, as we've got 7 marks here, it's usually 5, 6 or 7 marks. And it's always the same thing. It's writing an equilibrium out and then explaining what happens when you add acid and alkali. So it should hopefully be a question that you can prepare for, one that you can expect. Okay. This question then also asks us to do a bit of calculation. So here we're then making up our buffer solution with the methanoic acid, as we said, and we're mixing it with sodium hydroxide. So again, we've got two things we need to do. We need to explain why a buffer solution is formed, okay, and then calculate the pH. Okay. So a buffer solution is formed because if you mix these two things together, they're going to react, right? The methanoic acid reacts with the sodium hydroxide to form sodium methanoate. Okay. So that's going to be our conjugate base. Remember we said to make a buffer solution, you need to have a weak acid and its conjugate base. So there's the conjugate base, but haven't we just used up the acid? Okay. Well, the point here in this case, look, the acid was at a much higher concentration. So we had an excess of the acid to start with. So there's still going to be some acid left. Okay. But some methanoic acid still remains in the buffer solution. So this is the key thing. For it to be a buffer solution, you need to have methanoic acid and the methanoate ions. So you need to have both of these. Okay. So we've done this. Now we need to calculate the pH of this buffer solution. Okay. So to calculate the pH, we're going to need to use Ka. Okay. You always want to start off with your Ka expression. So here we've got our methanoic acid dissociating. And then if we want to calculate the pH, we're going to need the H+ concentration. So we can do the negative log of the H+. So we need to rearrange this Ka expression to get the H+. So it's going to be equal to Ka times the methanoic acid concentration divided by the concentration of the methanoate ions. And then we know what the Ka is from here. Okay. We don't know these two values. Okay. This is not the concentration of methanoic acid that we're going to use, because that was the concentration before you mixed it with the sodium hydroxide. So this is now going to be different, and we don't even have a value for this. Okay. So we need to work these out. So to do this, we need to work out what's going on with this reaction. We need to write an equation here. So because these two things are reacting with each other, we need the equation. So the methanoic acid is reacting with the sodium hydroxide. It's going to make the methanoate ions and sodium ions. You could write them together, but I'm going to write them separately just so the link is clearer. And it's going to make water as well. Okay. And then the way we work this out is we're going to use an ICE table, like we've seen if you've watched any of the videos about equilibrium. Okay. So we're going to look at how many moles did we have initially, how much do they change, and what do we have at equilibrium. Okay, we're going to do this in a table. Okay. I'll try and draw a straight line. And then we're going to need to convert these into concentrations before we put them into our Ka expression. So we need an extra row as well. Okay. And then let's split this up. One thing we can do straight away is just to look at our Ka expression and see what we're interested in. Okay, we don't care about water, and we don't care about sodium ions. We do care about this. We do care about the methanoic acid. And you think, oh, we don't care about this, but we do, because we need to use the values they've given us here to be able to calculate some other stuff. So we do need to worry about the sodium hydroxide, at least to start with. So that's where we're going to start. We're going to start with the initial amounts. Okay, so initially, how many moles of methanoic acid did we have? We're going to calculate it from here. Okay, so we had 200 centimeters cubed. So we're going to divide that by 1,000. So we're going to do 200 over 1,000 in decimeters cubed. And we're going to multiply that by its concentration, which was 3.2. So this is going to give us the initial number of moles. So we're going to do 200 divided by 1,000, and then times that by 3.2. So initially we have 0.64 moles of the methanoic acid. So that's going to go in here. And then we want to do the same thing for the sodium hydroxide. So we have, 800 centimeters cubed. So we can do 800 divided by 1,000. And we're going to multiply that by the 0.5. Okay. So that's what we're doing here. Let's just work that out. 800 divided by 1,000 and times by 0.5. And we get 0.4 moles of the sodium hydroxide. This is good. This should definitely be lower, because do you remember we said up here in this wordy bit that when these two react together, there's still some methanoic acid left over, okay, which is what we've shown. We've got more moles of methanoic acid. We had an excess, so that's good. That suggests we've done that right. So we know how much we had to start with, and we didn't have any methanoic ions to start with, because we just had these two things reacting together. So this would have started at 0. Okay. So then how are these going to change? Well, because we've got an excess of the methanoic acid, it means that all of the sodium hydroxide is going to react. So we're going to use up all of that, and we're going to end up with none, and then we're not going to bother at the end. So the sodium hydroxide is going to completely go. These react in a 1-to-1 ratio, as you can see. So if we use up 0.4 moles of sodium hydroxide, we're also going to use up 0.4 moles of methanoic acid. So we're going to be left with 0.24. And equally, we're then going to form 0.4 moles of methanoic ions. Okay. So now we just need to convert these into concentrations so that we can put them into our Ka expression. These are moles. Let's put the units on just so we don't get confused. That's moles, okay, because we got it from here, didn't we? And then worked it out. So we need to divide by the volume. What's the volume going to be? It's going to be 1 decimeter cubed. That's nice. So we're just going to divide by 1. So actually we don't really need to bother. Concentration is also going to be 0.24, but that's now in moles per decimeter cubed. And this is going to be 0.4 because we just divided by 1. So that's nice and easy. Now we're ready to go. We can substitute these values in here. So our H plus concentration is going to be the Ka value. Where was the Ka value? Right at the top, 1.7 times 10 to the minus 4. So it's going to be that. Multiplied by the acid concentration, which is 0.24. And then divided by the methanoic ions, which is 0.4. So let's calculate that one. 1.7 times 10 to the minus 4 times 0.24 divided by 0.4. And we get 1.02 times 10 to the minus 4. That's our H plus concentration. We want the pH. I'm running out of space here. I should have written a bit smaller. To get the pH, we're going to do the negative log of this value, aren't we? So then the pH is the negative log of 1.02 times 10 to the minus 4, which is, let's work that out. So we just do log of that answer and put a minus sign in front of it. So it's going to be 3.99. So that is our answer. Okay. So a lot of work there. Is 6-mark question though, although it did have this wordy bit in it as well. So this is probably 2 marks. I think all of this calculation bit is usually like a 4-mark question. Okay. So it is a lot of work to do, and this is why this topic is usually a bit of a tricky one. But we'll see some more examples of this type of calculation in the later videos.